Hello everyone, welcome to Mindspan Education. In this video, we are going to look at these two distributions, that is the chi-square distribution and the t distribution. And you know, these two distribution has already reflected in our last lecture, right? But first of all, let me just give you the overview of these two distribution, and then I will show you from the last lecture that where these two distribution that we have already introduced or they have already into our math, right? And from there we will pick and we will use this distribution to come up with few new things, right? But let me first of all just have a overview of these two distributions. So let's start with this chi-square distribution. So let's suppose if you have these random variables z1, z2, z3, z4 and till zn, and all these distributions, all these random variables are standard normal random variable and they are independent. So all these random variables are standard normal random variable, and since it is standard, then it will have the mean 0 and the variance 1. Now what you do, you simply square all these standard normal distribution. So you square all these normal distribution and then you sum up the square of the distribution. Then what you will get is a distribution that is chi-square distribution. And let me use this subscript here, k. So you have such k distributions, right? So this will, so what you have done, you have squared all these standard normal distribution and you have sum up the square of this distribution. Then the overall distribution of the sum of the square of the standard normal distribution will be a chi-square distribution with degree of freedom k. So this k is degree of freedom. df represents the degree of freedom, right? Or let me write the complete word for the first time. Right? And so if you take only one standard normal random variable and if you square it, right, then you will have a chi-square distribution with a single degree of freedom, or degree of freedom will be 1. If you take two such random variable, two standard normal random variable, and you square them and you sum up those random variable, you will have the chi-square distribution with 2 degree of freedom. And if you take the 3 standard normal random variable and square all these standard normal random variable and sum, then you will have the distribution that will be a chi-square distribution with 3 degree of freedom, right? So let's try to understand first of all that how or the plot of this chi-square distribution. So you have the PDF of the normal random variable, that is bell shape, right? That is of this kind, and it has the mean 0 and variance 1, right? And now if you try to look at, let's first of all look at this chi-square distribution with degree of freedom 1. That means you are just going to square this, right? Then how the distribution will look like? So if this random variable, that is the normal random variable, takes the value little z, right, and this little z is from minus infinity to plus infinity, then what are the values this z1 square will take? Obviously this z1 square will take the value that is from 0 to infinity, right? So whatever the value this z1 square will take, or the chi-square distribution with degree of freedom will take, the value that will be from 0 to infinity. So this chi-square distribution with degree of freedom 1 will always be positive, right? It will not take the value that will be negative, right? Always exist from 0 to infinity. Now let's try to look at the plot of this chi-square distribution with single degree of freedom. If this z, that is the standard normal random variable, takes the value from 0 to 1, so, or let's say from minus 1 to 0, so that means we are talking about this probability, or let's suppose this z takes the value from 0 to 1, that means we are talking about this probability, right? And if this z takes the value from within this range, then this z square, and that is nothing but the chi-square distribution with single degree of freedom, will take the value from 0 to 1. So that means z square taking the value from 0 to 1 corresponds to the probability of this event plus this event, right? If z takes the value from minus 1 to 0, or z takes the value from 0 to 1, that is equivalent to saying that z takes the value from 0 to 1, right? So happening of this event, that z square takes the value from 0 to 1, is equivalent to saying that probability of this event plus probability of this event. That means probability of this region plus probability of this region, right? So if we look at this plot of the chi-square distribution with degree of freedom from 0 to 1, so you will have the most of the probability here within this region 0 to 1. Why? Because in the normal distribution, most of the probabilities are from minus 1 to 1, right? And if you go to the extreme left or right, we have lesser densities of the probabilities, right? So for the chi-square distribution of degree of freedom 1, most of the probabilities will be from within this region, and as you go on, you will have the lesser densities of the probability, right? So this was the plot of the chi-square distribution with degree of freedom 1. Now let's try to look at the behavior of this PDF of the chi-square distribution if you have the degree of freedom that is 3. Now if you see, you can see all these individual probability, all these individual terms as a chi-square distribution with single degree of freedom, right? And all they can take the value from 0 to infinity, and this one also can take the value from 0 to infinity, this one also can take from 0 to infinity. Let's say if all these chi-square distribution takes the value from, let's say, 0 to 0.1, 0 to 0.1, and 0 to 0.1, and if you have to look at the overall, that the sum of these, so when all these takes the value 0, so this sum will take the value 0, and if all will take the value maximum, that is 0.1, then this will take the value that is 3 times 0.1, that is 0.3, right? So now if you look at a single chi-square distribution, so this probability, that is from that is from 0 to 0.1, this range of probability will get distributed over this range, that is from 0 to 0.3 for the chi-square distribution with degree of freedom 3. Now if you increase the degree of freedom 3, so, and all these are single chi-square distribution with degree of freedom 1, so these range of the probabilities will be getting spread over larger values of Z, right? So let me first of all show you the plot here. So this is the plot of different degrees of freedom for chi-square distribution. So for the k is equals to 1, this is the plot, right? And if you look at for k is equals to 3, this is the plot, right? So now you see for k is equals to 1, most of the probabilities are within this region, right? And as you increase the degree of freedom, the probabilities will be spread out over larger values of over the larger values, right? And as you keep increasing the degree of freedom, so ultimately the shape of the chi-square distribution will tend to take the shape of normal distribution, right? So this was just the intuition that how for the different degree of freedom we have the different plot for the chi-square distribution. Now let me give you the two important parameter for this chi-square distribution. The expected value of this chi-square distribution with degree of freedom k is same as the degree of freedom, and the variance of this chi-square distribution will be 2 times the degree of freedom. Alright, and I think that was the enough information for this chi-square distribution to go on for further that we will be looking. Now let's try to look at the t-square distribution or the student t distribution or the student t distribution. Let me first of all go through this t distribution. Let's suppose if we have this z, that is the standard normal random variable with mean 0 and variance 1, and this v is a chi-square distribution with k degree of freedom, and these two random variables are independent. Then the ratio of standard normal random variable and the square root of the scaled chi-square variable gives you the t distribution with k degree of freedom, right? And it will have the mean 0 and variance, that will be degree of freedom divided by degree of freedom minus 2, right? And mean will be 0 for degree of freedom greater than 1, right? And the variance will be this when the degree of freedom is greater than 2. So, and as we vary the degree of freedom, the shape of the t distribution will vary. So for degree of freedom 1, this is the shape of the t distribution, and for degree of freedom 3, this is the shape of the t distribution. And as we increase the degree of freedom, ultimately this t distribution will approaches to this normal distribution, right? And the very important point is that if you look at the distribution, t distribution with degree of freedom 1, then you see, so this is the tail, right? So the tail is heavier in comparison to the standard normal distribution. So standard normal distribution have this much of probabilities in the tail, but if you see for t distribution with degree of freedom 1, it has more probabilities, right? The tail is heavier than the standard normal distribution. and why it should be heavier for less degree of freedom, the tail, why it should be heavier, we have seen, or let me first of all discuss where we are encountering this t distribution. Recall when we constructed the confidence interval for the mean. So here, right? So if this sigma is known to us, then we just plug the sigma and you will have the confidence interval, right? The problem was that this sigma was not known, and what we have done, we have estimated this sigma, right? So now instead of using this sigma, we can use the standard deviation, the estimated standard deviation, that is S, right? But the thing is, as soon as you replace the known standard deviation with this estimated one, so you are introducing some extra randomness. Why? Because this depends upon the sample. If sample changes, this will change, right? So now if you look at here, so this was the random variable that was following or will have the shape of distribution that will be a normal distribution, right? So now if you replace this actual standard deviation or this sigma with the estimated standard deviation, so this S is itself a random variable. How? So this S square, so this one is random variable, right? So and so this S square will also be random variable, and if you look at this carefully, this is nothing but a chi-square distribution. Let's suppose if this estimated sample mean is 0, right, then you will have this x1 square plus x2 square plus dot 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 x3 square, right? And if all these are normal distribution, then this S square will be a chi-square distribution, right? So here now we have this, that is x bar minus mu, and this x bar is also a random variable, we have already seen, divided by this S divided by root over n. So this is random variable and this is random variable. Now this will not follow the, or we cannot approximate this using the standard normal random variable. It will have the distribution of the kind that will be t distribution, and if you look at even the expression, this is the t distribution. So if you take this as 0, so this is normal random variable, right? So the sample mean, so sample mean is a normal random variable divided by this S. So S is nothing but the root over square of the chi-square distribution and divided by this root n, right? So this is a t distribution, right? So here what we have is this expression. So this is sample mean minus the true mean divided by the estimated standard deviation divided by root n, right? So this is the sample mean, it has the normal distribution, and this is what, this is the root over of S square, and this S square is nothing but the chi-square distribution of the degree of freedom k, let's say k, right? So this will have the t distribution, right? Now there is one thing to point out, that this will have the degree of freedom n minus 1. So the sample and the degree of freedom is related like this. If you have n sample, then the degree of freedom will be n minus 1. Right? So this x bar is a sample mean, is a random. This sample standard deviation is also a random. So now your whole expression has two layer of randomness. This also depends upon the sample, this also depend upon the sample. So there are two layer of the randomness, and this is where the t distributions step in, and this account for the extra variability caused by eliminating this sigma from the data. So basically this t distribution is the corrected version of the normal distribution. So that is why this t distribution is wider and heavier tail, especially when the sample size is small. Sample size is small, that means the degree of freedom will be small, right? So if you ignore the fact that you are estimating this standard deviation or sigma and just use the normal distribution, let's suppose that just ignore this and use the just do not use the t distribution, use the normal distribution, right? So or even when the number of sample is very small, right? So your confidence interval will be too narrow and it will be also misleading. So by using this t distribution, you are being honest with your uncertainties. Now I think you must have got the idea that why we need to use the t distribution when the sigma is unknown. If sigma is unknown, then we need to estimate this sigma using the standard deviation, and this s is a estimated version of this sigma. And since this s is also causing the randomness, in order to account for that, we need to use such a distribution that can somehow manage our confidence interval. So that is why if sample size is less than, generally if it is less than 30, and if it is greater than 30 or the sample size is larger, then this t distribution and this normal distribution tend to have the same shape, right? But in general, if this sample size is less or less than 30, then the variability of the estimation of this standard deviation will cause some randomness, and in order to account for that, we are going to use a distribution that will have the wider shape than the normal distribution, and that will account for that variability caused by this estimated standard deviation, right? So I think I gave you the answer that from where this t distribution is coming from and what's the role of the t distribution in constructing the confidence interval. Alright, I think as of now, at this point, you should be clear about these two formula. Now since I have already introduced this chi-square distribution, and we are also seeing that this random variable, that is s square, have the distribution that is kind of chi-square distribution. So this is the point estimation of this variance, right? Can we construct a confidence interval for the variance using the chi-square distribution? Yes, we can do that. So now let's construct the confidence interval for the variance or for the standard deviation, right? This what we have seen is the confidence interval for the sample mean. Now what we are going to do, we are going to look at the confidence interval for the sample variance or the standard deviation, right? And it is clearly visible that it we will be using the chi-square distribution. Once we will go through that, then you will have the clear picture. Let's try to construct this confidence interval of the variance. Okay, now let's try to look at the confidence interval for the variance. We will follow the same procedure how we have described for the confidence interval for the mean, right? So let's suppose if we have these samples or these random variables that has been taken from some distribution, some normal distribution, so x1, x2, x3 and xn. So all these are independent, identically distributed, and they have been taken from some normal distribution. So this sigma square that we for that we want to construct the confidence interval. So this sigma square is the true variance, and this x bar, what is this? So this is your sample mean, and this sample mean is the estimate of the true mean, right? So true mean is mu. So this is sample mean. Given this sample, you have found this sample mean, and we have already seen that how we can get this estimate of the true mean, that is the sample mean, from this sample. But here what we want to do, we want to first of all estimate this variance. And how do we estimate this variance? So here I have already described you, right, how to estimate the variance, right? So last lecture I have already gone through. So this s square is the estimate of this true variance, and this is summation from I is equals to 1 to n xi minus the sample mean square divided by n minus 1. So this s square is the estimate of this true variance. Now what we want to do, we want to construct the confidence interval for this true mean. So let's start from here. Let's bring this n minus 1 to, so before that let me give you few connections from the chi-square distribution. So the chi-square distribution is the sum of, so let's suppose if these random variables are z1, z2, z3 or zn till zn, all these are normal random variable with mean 0 and variance 1. So all these are standard normal random variable, right? So we need to have the standard normal random variable, and then if we square and sum, then we will have the chi-square distribution with some degree of freedom, let's say k, right? So here what we can do, let's first of all try to bring this n minus 1 on the left hand side, n minus 1 s square, and here then we will have summation from I is equals to 1 to n xi minus x bar ka whole square. So but what we need is exactly, so all these are normal random variable, right? And it will have some mean. So we have subtracted the mean, right, from this distribution. That means we have done one step of the standardization, right? So the goal of the standardization is to bring the mean to 0 and scale properly so that the total variance is so the variance is 1, right? So we have already subtracted the, so the first step of the standardization we have, it has been already done. The second, what we do, we divide by the standard deviation, right? So overall, in order to get, so if you see this, so it has the square, right? It has the square. So overall, what I am trying to make is inside this, whatever the random variable will be a standard normal random variable, right? Because this is the requirement of the chi-square distribution, and if I achieve this, then I will be using this chi-square distribution to construct the confidence interval, right? So this is normal random variable with some variance or some mean. So the first step, the standardization, I have done it, but I need to also divide it with the standard deviation. That is the second step of the standardization. So I will divide with the standard deviation, and in order to manage both sides, I will have to also divide here the sigma square. So now if you look at what is this, so this is a standard normal random variable with mean 0 and the variance 1, right? And we are taking the square of it and we are summing it. So overall, this distribution will follow the chi-square distribution, and it will have the degree of freedom, that is n minus 1, right? So if you have n number of sample, let me also write this. So if you have n sample, then the degree of freedom will be n minus 1, right? Now I am going to use this, so I am going to use this chi-square distribution to construct the confidence interval for our variance, true variance, right? So how we have done that? Now we will have some distribution, right? So maybe the distribution will look like this maybe. So this is chi-square distribution. So this is the distribution that will look like depending upon the sample, right? So what I am going to do, I am going to first of all see this event, that the probability. So first of all, I will have to make the interval, so that, so let's suppose I am constructing maybe 90% interval, 95% confidence, or let's go in general. So so this is 1 minus alpha. What is this 1 minus alpha? So this alpha is the complementary of the confidence level, and this is 1 minus alpha is the confidence level. So let's suppose I am trying to make a confidence interval for 1 minus alpha, or if you think of an example, let's suppose you are trying to construct, that is 1 minus alpha is equals to for 95% interval. So this alpha will be 5%, right? So let me go in general. So I am trying to construct the confidence interval for 1 minus alpha. In order to that, now this will have the chi-square distribution. So in order to achieve 95% probability, right, so I will be looking for this particular event, that it, so basically I will be looking some interval such that the probability inside this interval is 95%, right? So or in general 1 minus alpha. That would be approximately 1 minus alpha, right? So here, if this is the point, that is alpha by 2, and then in order to get this 95% probability, let's suppose that this one is chi square 1 minus alpha by 2, since this distribution is not symmetrical, right? So here in the subscript we will be writing 1 minus alpha by 2, right? So if this falls within this interval, then this event will have the probability that would be whatever the desired interval for whatever the desired interval for we are looking for, right? Then so chi square alpha divided by 2, so and this will be chi square 1 minus alpha divided by 2, right? But what we are trying to find is that we are trying to look at the interval of this variance, right? So we can take the reciprocal here, and these intervals, this inequality sign will get changed, right? So here this will be sigma square divided by n minus 1 s square, and since inequality sign will get changed, here we will have alpha square, so chi square alpha by 2, and here we will have chi 1 minus alpha by 2. So what are these things? Well, these are nothing but the just critical points, right? And now what we can do further, we can simply multiply this n minus 1 s square. So we will have here n minus 1 s square chi this critical value divided by okay, I think what we have made okay, so here this will, if we are, so this will be 1 upon, right? Then divided by this critical value sigma square, and here we will have n minus 1 s square divided by this critical value. Alright, so this is the how we can construct the confidence interval for the variance, right? And if we have been asked for to construct the confidence interval for 95%, right, then we just need to look at, first of all, we need to also have the information about what is the degree of freedom, and we just need to look at the chi-square table, and by looking at the chi-square table for this 95% probability, we can have the numeric value for this interval, right? So we will take few examples in next video. So this is all about the confidence interval, and here is the summary. So if sigma is known, you can just use the normal table to find this critical value, and then you will have the confidence interval of whatever you the confidence interval you are looking for. and if sigma is unknown to us, you need to estimate the standard deviation, and in that case you will have to use the t table. And if you are looking for the confidence interval of variance, right, then in for that you will have to look up the chi-square table, and if the sample is n, for the t and chi-square, the degree of freedom will be n minus 1, right. And let me ask you the last question: how do you interpret this confidence interval? Does it mean that if I am looking for 95% confidence interval, then does it mean that the variance will lie within this confidence within this interval will have the probability 95%? No, this is the wrong interpretation. Let me know in the comment section what is the true interpretation of this confidence interval of the variance. We have already discussed for the sample for the mean, right, for the population mean. Give me the interpretation of the variance as well, right? All right, next video we are going to look up bunch of problems based on the concept that we have discussed so far regarding this confidence interval, and then we will be left with only one topic, that is the few test like z test, chi-square test, and the t test. Then we will be done with this probability and statistics. Thank you so much.